low pass, on bandpass, low pass transformation, and we discuss everything about these questions. Okay, I think we can start. Oh, right now we have 6. I will scream if something happens. Yes, yeah, thank you. Okay, let's start in a few seconds. Okay, welcome on our tutorial for communication engineering. Thank you for coming to our early morning tutorial. And today we're going to continue solving different tasks on from our list. And second part of questions already available on Moodle, so please check. I have already uploaded some cheat sheet and some nice animations to Moodle webpage, so you're also welcome to check them and use information provided. And please interrupt me if you have any questions during our discussion. And as I told you, we're going to discuss today low pass, band pass, low pass transformation. Okay, and for those who are listening us online, please write your questions in the chat. If you need your answer immediately, you're also welcome to just open your microphone and ask your questions directly. And if there are any questions and doubts, please ask them. Okay, we start our discussion by trying to solve a very simple question on bandpass low pass transformation. And we consider the following problem. The updated set of tasks will be slightly different, but here we consider old version of questions. And the first question was the following: that you have signal, let's say sine, and then the signal given in bandpass range. And the question, you need to find a representation of the signal in low pass range. So let's try to solve this problem. And yeah, let's try. Let's see how it works. So we have the following question. We need to determine the complex Okay, I changed some settings, and if you cannot hear us, please let me know, because yeah, we're still not sure how it works. So determine the complex envelope for real valued bandpass signal. And we have the following signal. We consider case B, where we have sinusoid. And maybe close the door. So as I said, we consider sinusoid. And you can do the same for cosine and for the rest, for the remaining part by yourself at home. Here I just show you idea, and I think you also did it on lectures. So, and this is signal in time domain. And what we do at first step, we convert the signal in frequency domain. And for sine, it's just very simple transformation. You have sine. After transformation, you have in frequency domain 2 delta pulses. And they have imaginary amplitudes because they consist of sine components. What's again, question for you, what's the difference between the real spectrum and imaginary spectrum? Please don't say that imaginary spectrum is not implementable. What it means that you have reals. Yes, it's just exactly. If you have real spectrum, it means that this spectrum represented by cosine wave, cosine component at some frequency. But if you have imaginary component in your spectrum, it just means that it's represented by cosine wave shifted by 90 degree, or it means that it's just represented by sine. But it's absolutely fine. You can, of course, implement it without any problems. So, and here we have pure imaginary spectrum, which includes two frequency delta pulses. And we can write it as U0 over 2J times delta pulse at frequency F minus Fc minus delta pulse with amplitude U0 over 2J delta F plus Fc. And now we can start working with this spectrum. So first of all, I make a small picture of this spectrum. And I schematically show these two delta pulses. So one delta pulse should be in the range of positive frequencies. Another delta pulse must be in the range of negative frequencies. And here in positive range, we have amplitude U0 over 2J. And in negative range, we have delta pulse means magnitude amplitude minus U0 over 2J. Okay, and this is our spectrum. So, but there is a question. I have very real question. If you look to our cheat sheet, you see that somehow order or amplitude of the sign of delta pulses is different from what I did. And my question, why? There is mistake. Do you see the problem? Somehow it was flipped. And we have the same in our notes. In time domain. In time domain, I mean, yeah, the same. Oh, sorry? And what's wrong with J? Aha, yeah, you're right. Because just take a careful look to this expression. In on our screen, J comes in denominator. But in your cheat sheet, it comes in the numerator part. And as a result, when you multiply by J, you have additional minus sign. So there is no mistake, but just depending where you place J, sign also varies. Okay, fine. And now let's try to perform our transformation from band pass range to low pass range. And what we actually do, we do very simple steps. First step that we do in order to perform a band pass low pass transformation, you cut all negative frequencies. You just remove them completely. I just remove all components in negative range. And I repeat the same plot, but without negative frequencies. So now I have only one component, delta pulse at frequency Fc with magnitude U0 to J. Okay, fine. And next step that we're going to do, we're going to shift our delta pulse by the frequency with respect to we perform bandpass low pass transformation to 0. And here is important important. I should point your attention that depending on the frequency with respect to which we perform transformation, you may have different results. And here we perform transformation with respect to frequency Fc. As a result, we move this delta pulse from carrier frequency Fc to 0. So, and then we get that we have delta pulse at origin at 0. This is our delta pulse. And it has magnitude U0 over 2J. And my question is it the end? Should we stop here or should we do something, some additional step? And another question, why? In general, we already get something in low pass range. But the question, is it the final result or? And I believe you discussed this question during lecture. Or maybe my question, what may be the problem if we leave our delta pulse as it is right now? It's constant. No, I mean, okay, it's constant, but it's not the biggest problem that we have. I mean, it's just delta pulse. Sorry? Okay, yes, good point. But even if, okay, we do this, we convert it to time domain, but even if we convert it to time domain, we have some problem here. We have some problem. Yes? We need... No, we removed it. We don't have any frequency components anymore. We just shifted to 0, and we have just delta pulse at 0, and that's all. No, we don't need. I mean, the problem that, remember what we did. We started with signal which included 2 delta pulses, yeah? And if you calculate what's the energy of original signal, U2, how we calculate energy? You take squared value of magnitude for original signal and calculate sum of all frequency components. Yeah, let's try to do this. We have absolute value squared. We have U0 over 2. I omit imaginary part plus. This is for, let's say, positive delta pulse. And then we have U0 over 2 squared. It's for negative delta pulse energy. And as a result, final energy will be U0 squared over 2. Yeah? And let's try to calculate the energy of the final result that we get after we perform this transformation from band pass range to low pass range. So not U, but energy of U2, and let's say L. No, it's not L. It's not final answer, but let's say prime. And then we have delta pulse U0 over 2 squared, and we get that energy equals to U0 over U0 squared over 2. Sorry. And you see that original energy was U0 squared over 2, and resulting energy U0 squared over 4. So after transformation, somehow you changed energy. So energy of resulting signal is different from what was original value. And this is the problem, because energy must stay constant. And in order to ensure, I will put the positive part to 0. Okay, let me just complete and then we repeat again. So in order to make sure that energy stays the same, we have to normalize resulting signal. And how we normalize this signal? We multiply it by square root of 2. Because we cut energy by 2. And as a result, we have to increase amplitude by square root of 2 to keep energy the same. So for this reason, I multiply this signal by square root of 2. And this is the final amplitude for our signal in low pass range. So, and finally, I show final result. No, maybe I should. Finally, I show how it should look like. Have delta pulse, bigger magnitude, and it has value square root of 2 over 2j times u0. This is our signal in low pass range. U of f, and we can place L, low pass range. So why we shifted, why we shifted delta pulse to 0? Because here we perform so-called band pass to low pass transformation, band pass to low pass transformation with respect to FC. This is your reference. You use gyro frequency FC as a reference with respect to which we perform this transformation. It can be written that it can be given different frequency, and then you have to perform slightly different shift by the value that provided for you in the task. This reason we perform this shift. Okay, any questions? Any questions about this stuff, about this transformation? And whenever we ask you about low pass, band pass, low pass transformation, you do these steps. You cut negative range, you shift your remaining part by reference frequency, and then you normalize. And whatever you get, it will be your low pass signal that you need to have. Okay.
Oh, sir, I have a
Okay, yes,
question.
there's question. Yes?
Sir, why have you multiplied by root 2? Kindly repeat it again.
Yes, we multiplied by square root of 2, because if you don't do it, then input and output signals will have different energy at low band pass, low pass transformation, and vice versa. They keep the same energy of signal. They doesn't change energy of signal. So if you take signal in low pass range, it must have exactly the same energy as it would have in band pass range. And in order to ensure that energy stays constant, we multiply by square root of 2. Okay, and my final question. This is, as one of you pointed out, this is signal in frequency domain. But how the signal will look like in time domain? How it will look like in time domain? Come again? No, it's not step. It's a constant. And what's the amplitude of this constant? Please louder. Not exactly. I mean, you forget J. J also comes as amplitude. So, signal in time domain after low pass transformation, UL2 of T, it will be pure amplitude, but only for this case, because delta pulse in origin, 2J times U0. So it's imaginary amplitude, but again, it's because a low pass range is because we don't have sine or cosine to indicate our phase, and we use complex numbers to hold this information about what's the phase of our signal. And again, imaginary part is not a problem at all. Imaginary part just indicates you that something what you have there is shifted by 90 degrees. That's all. So, yeah. Just line. No, not step. It's just line that comes from minus infinity to infinity. Okay, let's plot it, but it's very simple function. So it's UL2 of t, of course, and then it just goes from just line. And you can specify amplitude of this line, square root of 2 over 2j u0. That's all. Okay, fine. That's all for this task. And we go to next one, because other parts, they're not so interesting for us. Okay, now we go to the following task. I using old numbers, and I think they're different from what you can find on Moodle. So we consider the following problem. This is our function, and this is our spectrum of our signal. And we need to draw this spectrum in the corresponding low pass range. And we perform transformation with respect to frequency fc. And then we need to determine signal in time domain. So first we have spectrum in the bandpass range. We perform bandpass low pass transformation, and then we need to find signal in time domain of the resulting low pass signal. Yes, you can find these questions on Moodle. We placed them yesterday evening, and you find there this tasks repetition for signal and systems, and below you find the second part. It's not a problem. It's better for you because then you have different questions. In the end, we're not going to solve all tasks, but we're also going to show you what you do when you have different tasks. Because also for exam, you have different set of questions. And your task is to get idea. Okay, but anyway, let's try to do this. But I think it was there, at least yesterday, checking it was there. But even if it's not a problem. So let's do it. So we have the following spectrum. We have two triangular parts. First part. Second part is our spectrum, x of f. See domain. We have amplitude equals to x0. And then we have these triangles located at frequencies fc and minus fc. And have frequency range equals to b. Okay, my question, do you have real or imaginary spectrum, and why? Yeah, because it's even, and you don't have imaginary numbers. Yeah, it's right. We have pure real spectrum. Okay, and now we need to perform low pass band pass transformation. I will do it. Actually, I just show you answer. So we can do all these steps on the same plot above. So here we should get our spectrum in low pass range. Origin, and again, we perform transformation with respect to carrier frequency fc. So first step that we do, we cut negative frequencies. We just remove them. We don't have them anymore. First step. Second step, the remaining part in positive range of frequencies, we move by the frequency regarding to which we perform transformation. And as a result, we get that we have signal at origin that goes from minus b over 2 to b over 2. And what's the amplitude? Original amplitude was x0, but it's not, as we mentioned, it's not the end. We have to do some changes. And what will be the final amplitude? So we multiply by square root of 2. Because if we don't do it, energy of signal will be 2 times smaller. So times square root of 2. Okay, now this is our signal. This is our spectrum in a low pass range. And now we have to calculate signal in time domain. This is our spectrum, and we have to calculate inverse Fourier transform and find signal in time domain. So we calculate inverse Fourier transform, and we have to get something in time domain, in low pass range and time domain. Okay, unfortunately, we don't have such function in our nodes, and we have to calculate inverse Fourier transform explicitly. Yeah? And let's try to do this. So we start that our signal in low pass range and in time domain, we find as inverse Fourier transform that we calculate using integral from minus infinity to infinity of our spectrum multiplied by exponential function. So now we have to calculate this integral explicitly. And we can substitute all what we know. We know that our integral will go from minus b over 2 to b over 2. Why? Why you reduce the limits from infinity to b over 2? Because it's 0 outside. It just doesn't make any changes because it's just we integrate 0. Yes, it was correct. And now we have our signal in frequency range 2 pi ft. No, it's of course df. No, it's because it was typo. Because we have to find signal in time domain, and we have in frequency, we integrate all frequencies. No, it was typo. Thank you. And now we have to somehow formalize our picture. Yeah, this is how our signal looks like. And now we have to give explain what it is. So let's try to do it step by step. Try to formalize this line and give. First of all, how can we formalize this plot? It is a line, yeah, it's a line that we consider in the range from minus b over 2 to b over 2. We can just say that it's a line that goes from minus infinity to infinity, but our region of interest goes from minus b over 2 to b over 2. And now we just need to explain, to write equation of this line. So how we do this? We first of all write what we know about this line. We know that at this line at point minus b over 2, and then we write general equation for a line. But what's the general equation for a line? It's a times x plus b equals to y. Yeah, this is general equation. And now we know that x equals to minus b over 2, and we know what's the result. It's 0. We know that a times minus b over 2 plus b equals to 0. This is our first point. And also we know second point. We know that at b over 2, which equals to a b times b over 2 plus b, small b, equals to what? Equals to amplitude. And amplitude is x0 times square root of 2. This is our amplitude. And now we need to understand what is A, what is B. We can subtract. Let's name first line as first equation, second line as second equation. And what can we do? We can subtract from second equation first one, and then we get that A times capital B must be equal to x0 times square root of 2. Okay, and from there we see that A equals to x0 over capital B times square root of 2. Okay, now we know what is A. And if we want to find B, we have to calculate sum of second and first equations. Then we get that we have 2b, 2 small b equals to x0 times square root of 2. Okay, and from where we find that b equals to x0 times square root of 2 over 2. Okay, and now finally we can write the whole equation for our function. So it will be that we have x0 over b times square root of 2 times, it was f plus x0 times square root of 2 over 2. And this is our equals to xl of f. And we also say that f comes, it's f in the range from minus b over 2 to b over 2. This is our range for f. Okay, let me check. Square root of 2, x0 over b, f. So it's correct answer. Okay, and now we need to calculate integral. So we substitute this expression in our integral. Integral from minus b over 2, b over 2. Then we have our function that is x0 over capital B times square root of 2 times f plus x0 times square root of 2 divided by 2 times exponential function j2 pi f e f f. And now we need to resolve, we need to calculate this integral. We can rewrite it. We can move outside integral constant x0 square root of, let's write square root of 2 times x0 times integral from minus b over 2 to b over 2. Inside we have 1 over b times f plus 1 over 2 times exponential function j2 pi f t df. Now we need to calculate this integral. But the problem that you don't have it's not tabulated integral. We have to use some hints to calculate it. And here we use the following hint that you remember that if you have integral u times dv, you can represent this integral as u times v minus integral of v du. And sometimes it helps us simplify calculations. This is what you're going to use here. We say that, let's say that our exponential function and f, it will be dv, and the rest part will be our u. So we say that in this case we say that okay, let's try to define. We can just say that u equals to the whole expression inside parentheses 1 over b f plus 1 over 2. Okay, then we have that du equals to 1 over b times df Okay, and then we have second part, dv equals to exponential function j2 pi ft f. And if we want to calculate v, we have to calculate integral of dv. And for this exponential function, it will be equal to 1 over j2 pi e times exponential function j2 pi ft. And if you see that I made some typos or mistakes, please just indicate it. Okay, and now we can write how our integral. And what did I forget? We have to somehow modify limits. How should we modify limits? Because they don't stay the same. Yeah, after these changes, what happens with limits? Any ideas? Limits. I mean, should we change limits of our integral, or should we keep them the same? And if we should change them, then how? How should we change limits?
We just multiply by 2 and integrate from 0 to p over 2.
Multiply. Should we multiply by 2?
We can multiply.
I think we should take our limits and substitute in our expression where we explain how we replace this variable. Yeah, am I right? Or not?
Yes. I don't know.
Yeah, let's do it. So you have first limit that f goes to, or not, okay, not goes, but equals to p over 2. Yeah, and then you substitute this expression above. And then u, it leads us to u that equals to b over 2 times 1 over b. It will be 1 over 2 plus 1 over 2. It will be 1. Okay, good. Then let's take another limit. F equals to minus b over 2. And then we substitute this expression in our replacement. We have minus 1 over minus b over 2 times 1 over b. It will be minus 1 over 2 plus 1 over 2. And u, it means that u must be equal to 0. Yeah? Yeah, just let me know if you don't agree with me. And as a result, we can rewrite our integral, and we can write it as but 1 second. But did we need it? Because then we still have 1 over b. Okay, maybe we don't need it because we don't make this replacement. We don't. Okay, yeah, because we don't use u, but we replace it back because we replace it back. Okay, yeah, it was redundant step because what I do next, I just write it in original terms. But you would need this step if you would keep u, if you don't make the replacement back. But okay, you have exponential function j2 pi ft times 1 over b. No, not 1 over b. I know, yes. 1 over b times f plus 1 over 2. Then you have these two limits. Now we substitute all two values. And then we have minus, and we have the following: integral from minus b over 2 to b over 2, 1 over 2 pi f to j 2 pi t times 1 over b times exponential function j2 pi ft times df is our. Okay, let's try to understand what happens with the first part. So if we substitute b over 2, b over 2, let's try to check what happens in this case. One over j 2 pi t times exponential function j 2 pi b over 2t, and then we have times 1 minus, and when we substitute minus b over 2, we will get 0, because inside this parenthesis we will have minus 1 over 2 plus 1 over 2, and it will be equal to 0. Just don't write anything. And then we have second part, 1 over j 2 pi t times, let's write it separately, 1 over capital B, and then we have this is just exponential function. Yeah, we just calculate integral of an exponential function, 1 over j 2 pi 2 pi t times exponential function j 2 pi f t. Then we have to substitute lower limit minus b over 2 and upper limit b over 2. Okay, and we get that we have 1 over j pi t times exponential function j 2 pi t over 2 t. I make a mistake. Yeah, I make typo.
Yeah.
No, it should be plus. Do you mean this minus for exponential function? Let's try to check it. Okay, we did replacement, so we have here x. And I forget x actually. Okay, then we made this replace. Have u is our e plus 1 half u. Okay, it's 1 over. Then v. When we calculate integral, it's 1 over j 2 pi t exponential function. Fine. And now we go further. So we have 1 over bf plus 1 half times exponential function. Okay, when we substitute upper limit, we have b over 2 times. Okay, fine. Times 1 minus, and then we have, when we substitute over, we have 0. No, it's have 1 times 0. It's, no, we have minus b times, yeah, times 0. It's fine, and it should work. And then we go further. So we have minus 1 over j 2 pi t times 1 over b, 1 over pi t, so j 2 pi ft, and then from minus b over 2 to b over 2. So then we have minus. So we can just multiply j times j, it will be plus. Then we have 1 over b times 1 over 4 pi squared t squared times, and then we have exponential function j 2 pi f t over 2 minus, actually I put parentheses because expression in front of it will be the same, minus, and then we have exponential function minus j 2 pi f t over 2. And here we have two parts. It equals to, we have exponential part. And then also we have this second part. And here, this difference of two exponentials, we can, using hint from previous tutorial, we remember that it will be exponential alpha, j alpha, minus exponential minus j alpha equals to cosine plus sine minus cosine plus sine. It will be 2 times sine alpha. And as a result, we can rewrite it and we get the following. We also actually open exponential function. Exponential function we open as cosine plus j sine alpha. Yeah, and as a result, you will get that we have 1 over j 2 pi j 2 pi ft times cosine of 2 pi capital B over 2 times t plus 1 over 2 pi ft times sine 2 pi capital B over 2 times t, and plus 1 over capital B 1 over 2 pi squared t squared times sine, then we have 2 pi f 2 pi capital B over 2 times f. This is what we get.
Hello.
Yes.
Yes, sir. Sir, e to the power j alpha minus e to the power minus j alpha should be 2j sine alpha. It should be
So
2j.
in the end, it should be 2 sine.
Means
Do you mean
sine alpha is e to the power j alpha minus e to the power minus j alpha divided by 2j.
Okay, I forget
J.
J. Yes,
Yeah.
yes, you're right. Of course, we also have J. We have 2J. Yes, you're absolutely right. And as a result, we have to also write this J in our final answer. So it should be J divided by 2 pi squared. Yeah, like this. Yeah, and then we have this J. Okay, so now we can actually reorder slightly our, and yes, and remember, I forget to write 2x. I forget to write this part. So I have to actually place this square root of 2x0 everywhere. Square root of 2x0, and we multiply. Square root of 2x0 multiply the whole expression. J2 pi, and we don't have f. We don't have f because cross type. We don't have it above, and we don't have it here. And also I made the same mistake. So it should be just 2 pi t, 2 pi squared t squared. Okay. Now we can just try to combine real parts and imaginary parts separately. Write them separately. So we have square root of 2x0 times real part 1 over 2 pi t times sine 2 pi capital B over 2t. And then we have minus square root to 2x0 times, we can place j open parenthesis, minus j, then we have square root of 2x0 times 1 over 2 pi t. 2 pi t times cosine 2 pi capital B over 2t. And then we have what left? Minus 1 over capital B times 1 over 2 pi squared t squared times sine 2 pi capital B over 2f. Yeah. Oh, what should I do? Okay, yeah. Yeah, it's not f, it's t. Yes. Yeah, you're right. It's true. Yeah. Thank you. So finally, we get that we have two parts. We have one part which called as in phase, and second part without imaginary component. Should actually place write as plus, I believe. We should write as plus, then we should put minus inside. And second part we call as quadrature component. Okay. I just correct if we get what we're supposed to get. If I didn't forget scalar, looks like that I forget. Yes, I forget scalar because I had to multiply by square root of 2x0 also second part, and I didn't do it. So let me rewrite. I have to write it as square root of 2 times x0 t times 2 pi squared t squared. Cool. Yes, you see that it's very easy to make very small mistakes, like forget scalar or like get sign. And I really want to point your attention so that you'll be very careful by writing your solution during exam, because we subtract points. Yeah. Yeah, you see that even I also did typos, but also I would like to ask you to be careful while you're writing your answer, because as I said, it's easy to make a mistake. But in the end, you had to get this result, and there are different ways how you can get this result, because you can choose different parts for replacement while you calculate integral. But during exam, you don't need to show all intermediate steps. If it's written that you need to find answer, you have to get this answer as fast as possible. And I show you all these steps on during tutorial, just to be sure that you understand what we are doing, how we get this answer. But you don't need to show them for your solution. Yeah? Okay, are there any questions? And we still have 30 minutes. Okay, if no more questions, let me check chat. I think there was something in the chat. Okay, yes, already mentioned that I forget J. Thank you for seeing this. And now we go to next task. The next task. Okay. For the next task, We just go to the next one. So the task is the following. So we have a complex baseband signal, and it's low pass range signal, and it's given by this expression, and it's this x subscript L of t equals to psi function, and we need to calculate corresponding bandpass signal x of t if the carrier frequency equals to 5 times b. And then we need to determine the spectrum of this bandpass signal. Let's try to do this. Two pi b capital B over 2 times t. This is my 2 pi. This is like just pi, but it's 2 pi. 2 pi b over 2. So let's go further. Okay, let me just check again that it should be this. It should be exactly this answer. To pt x0 sine, and then we have this minus x cosine, also fine, and we have plus. Oh, it should be exactly this answer. So, and if you find some misconceptions or if you have any questions, please ask them. Okay, now we go to next question. So we have the following signal in pass range, low pass range. So it's x of L of t, and it equals to j x0 times psi function. Psi function pi capital B t. This is our signal in low pass range. And we need to calculate signal in band pass range, x of t, question mark. And when we calculate, we assume that carrier frequency equals to 5 times capital B. And there are different ways how we can do this, but let's try to just follow the following procedure. First of all, let's try to visualize signal itself in time domain and the corresponding frequency, the corresponding spectrum in frequency domain. So we have XL of t, then we have t, x is for time, and we need to show psi function. Psi function, and what's the value of point where we cross 0? What should I put for this point?
1 upon b, 2 upon b, and so on.
Sorry, can you repeat again?
Sir, it should be plus minus n upon b. Means plus 1 upon b, then 2 upon b, then 3 upon b. Same thing in the left coordinates.
Yes,
Left
it's
half.
multiples of 1 over b.
Yeah.
Yeah, it should be multiples of 1 over b. At first point, it will be 1 over b, then it will be 2 over b, and so on. So it was absolutely right. Minus 2 over b, and so on. So this is how our time domain signal looks like. And amplitude will be j times x0. Okay, then after transformation, what should we get after transformation in frequency domain? How the corresponding spectrum will look like? It's rectangular function. Yeah, it will be pure rectangular function. And what's the range of this rectangular function? What's the range?
Minus b by 2 to plus b by 2.
Yes, exactly. It will be from minus b by 2 to b by 2. And then the second question, what will be the amplitude? Will it be the same or will it be slightly different? No, not the same. Slightly different. And here is our, this is how we transform. Yeah, we have rectangular function, and this is our sine function. But if you have psi function and you go to rectangular function, you have to normalize it. But remember that now we have psi function in time domain. Okay, what will be the amplitude in frequency domain? Any ideas? By b, yeah, we have to divide by b. So resulting amplitude will be jx0 divided by b, because b defines the range of our rectangular pulse, or it also defines our psi function. Okay, great. And now we do the following. So we can actually write our function that xl of f can be written as 1 over b times jx0 times rectangular pulse f divided by b. Okay, but still I have questions, some questions for you. What's the meaning of, again, why we have j? What's the meaning of j in our original low pass signal? For some reason, our signal in the low pass range contains imaginary number. And how would you interpret this imaginary number in amplitude? Would you interpret somehow this imaginary number?
Quadrature component.
Yes, it's all the same. I mean, there is nothing different. It just means that you have shifted by 90-degree cosine frequency. But I mean, I just want to make sure that you, all of you, understand it by heart. Okay, let's go further. Now we have to reconstruct our time domain signal in bandpass range. And we can do it very easily if we just follow the following expression, that time domain signal you can reconstruct from two parts of your low pass signal. You take real part and you take imaginary part, and you multiply each part by cosine and sine carrier frequencies. So I just write in, you have xl prime of t times square root of 2 times cosine 2 pi fct minus xl double prime of t times square root of 2 times sine 2 pi fct. Okay, and xl prime of t is nothing else as a real part of our signal in low pass range, and xl subscript l double prime of t equals to imaginary part of our signal in low pass range. So now you just need to plug everything what you know, and you get signal in band pass range. And for our case, we can do it easily because our signal is purely imaginary. So we don't have real part. And as a result, we get that we have only second part. It will be xl of t is given by, okay, let me write, I first write the scalar square root of 2. Then I will write x0, and then I write sine psi pi capital B t. And last part, I have to write carrier frequency. sine 2 pi. And we also mentioned in the beginning that carrier frequency equals to 5 times capital D. This is our carrier frequency. And we also plug this value. We have 2 pi times 5 times capital B times T. This is our carrier frequency. It's 5 times capital B because of the following. Calculate the corresponding bandpass signal x of t if the frequency fc equals to 5 times capital B. So it's given in the task, but if it's not given, then we just keep it as fc. It's also fine. It will be just unknown constant. Because effective energy of sine, if you calculate energy of sine wave, it will be u square divided by 2. If you take rectangular pulse, and if you take sine wave the same duration, energy will be 2 times smaller. And then you have to multiply to keep it the same, comparing to low pass signal. And it's all the same, just because after you moving back, you have to, and you multiply by sine wave, you have to make sure that your energy will be the same. Effective energy of sine will be 2 times smaller. This is a problem. Okay, and so I think it was it all. Oh, now we need to determine spectrum. We need to determine spectrum. So now we have to find. Now we have signal in time domain. No, wrong. We have signal in time domain, and we need to calculate signal in frequency domain, x of f. And then we have what we have. We have signal which includes 2 parts. And we have to calculate Fourier transform of this signal. And we also discussed last time what we do if we have, if we need to calculate Fourier transform of product of 2 signals. We calculate Fourier transform of each part separately, and then we take convolution of resulting parts. So we calculate Fourier transform of psi function. We calculate Fourier transform of sine function, and then we calculate convolution between these both parts. So let's try to do this. For first part, we have scalar that we shouldn't forget. It will be square root of 2 times x0. Then for psi function, we already have it, yeah, because we did it before, and we get that the result will be 1 over b times rectangular pulse. This is, I write here, 1 over b times a rectangular pulse, pi, no, not pi, f over capital B. And we calculate convolution, the second part. And for second part, we have Fourier transform of sine wave. And for sine wave, we already did it today, but here we have this also hint, how it looks like. And I write it in this way, that we have 1 over 2j delta pulse f minus 5 capital B, I should place parentheses, minus 1 over 2j times delta pulse f min plus 5 capital B. And now we calculate convolution between the rectangular pulse and our 2 delta pulses. So it's very easy to calculate because we simply replace our delta pulse by rectangular pulse, and we get that we have square root of 2 minus square root of 2. I shouldn't forget other scalar. So we have square root of 2 divided by 2j times x0. Should I write x0 divided by capital B? And then times rectangular pulse at frequency f minus 5 capital B divided by capital B, and plus square root of 2 divided by 2, okay, x0 divided by B times rectangular pulse, and then we have f plus 5 capital B divided by capital B. And to make it nicer, we can multiply both parts by j, multiply and divide in order to make it the same, be consistent. And this is how we change sign. We have j divided by square root of 2 this plus times x0 divided by b times rectangular pulse f minus 5b divided by capital B. And then we have minus j over square root of 2 times x0 divided by capital B, rectangular. We have f plus 5b divided by capital B. That's all. We just need to make a picture of this plot and of this spectrum, and that's all for this task. And picture is very simple because you just have two rectangular pulses, one in at frequency 5B, another one at frequency minus 5. You just need to show approximately. I should make it larger. This is our 5B. 5. And then we have range equals to B. Our rectangular pulse with amplitude j over square root of 2 times x0 over B. And we have another rectangular pulse at minus 5B, and we have amplitude minus j over square root of 2 times x0 over capital B. This is our final result. This is x of f. This is our frequency. Okay, but you could also get the same result. You could also get the same result. You could get this spectrum simply from spectrum of low pass station. We could start with signal in low pass range and spectrum for this signal, XL of f. This is how it looks like. It's j x0 over b. And then we have to reduce energy because we're going to double this signal, and as a result, we will double energy. And in order to keep it the same, we have to, in this case, divide by square root of 2 because we increase number of components in our spectrum. So we perform. So here we're doing low pass to band pass transformation. Low pass to band pass transformation. Then we change amplitude, we decrease it, and divide by square root of 2. So we have j x0 over b times 1 over square root of 2. And then you need to double number of components. And again, you move this component to the range of positive frequencies, and you place it to the frequency with respect to which we perform transformation. In our case, it will be 5B. And the second part, yeah, this is just straightforward. We had component at positive, at 0, and then we move first part at positive range, as it is. But then what happens with the component that we move to the negative part? So answer that it depends. It depends on what kind of spectrum you have. If you have imaginary spectrum, then resulting spectrum must be, it must be this, I forget this word, not symmetric, but it's odd call. Yeah, it's odd. It should be odd. Yeah, it should be odd if you have imaginary spectrum. But if you have real spectrum, the result must be even. Then depending on what's your spectrum in low pass range, you do this different transformation. Because in our case, we have pure imaginary spectrum in low pass range. As a result, we have to move it to the negative range with negative amplitude. So we place it at frequency minus 5B, and then we revert amplitude at minus J x0 over B times 1 over square root of 2. You can also get exactly the same result, just operating with spectrum of low pass signal in low pass range. It also works, but again, there are different ways how you get the same result. So yeah, you can choose any of them. Maybe you can also say that, but it would look like as this if you would have pure real part, if x of L would equal real part. So depending on what you have, you get different results. Okay, I think there was question. Chat. Asymmetric. Yes, you're right. Thank you. Okay, let's go further. Okay.
I have a question.
Yes. Are there any comments?
Yeah, I have a question. I want to know why this is in third quadrant and not in the second quadrant.
Why did I place green in second orthant?
Yeah.
Because you would have this spectrum if you would have pure real signal in low pass range. If you wouldn't have this imaginary number that we have in our example, without this imaginary number, without this J, you had to place your signal in second orthant, but not third as we do it now. I show you just options that we could have. Yeah.
Okay. Understood. Thank you.
Yeah, no problem. Okay, let's go further. Are there more questions? Yeah, no problem. This one. Yeah, this is right, that you have one signal and then you split it for two, but you split energy. You split energy for two, not amplitudes for two, but energies. And amplitudes it will be square root of energy. And for this reason, we have square root of 2, but not simply divide by 2, because we are caring to have the same energy before and after. Not the same amplitudes, but energy. Yes, this is intermediate step that this was our original signal. Then we normalized energy so that two components with such amplitudes will have exactly the same energy as we had for original low pass spectrum. And then we just use these modified amplitudes for our resulting components in positive range and negative range. It's just intermediate step. I don't know if we can give a name like it's kind of in low pass, with modified amplitude, but we don't have special name for this signal. It's just for your information to just understand what happens. Okay, good. Okay, let's see what we have. There are more questions. Okay, sorry, yeah, I should repeat questions when you ask. The previous question was, as I understand, what's the meaning of this middle plot, yeah, and how can we name that? How can we name it? I answered that it was just intermediate result where we normalize amplitude to make it in further steps, yeah, but we don't have a special name for this plot. Usually we just name this first plot as spectrum in low pass range, and we have plot resulting plot, which is spectrum in band pass range, which we can code as x of f. And that's all. Of course, we can have multiple intermediate steps, but we don't give names for them. Okay, no, I don't think that we should go to task number 7 because it is too big for today. Still have 10 minutes. Okay, let me check what else can we try to solve. Okay, we actually quite a good shape. We were able to solve 3 on tasks. Okay, let's maybe try to solve task number 4 from my old notes. But I think it's very simple because it's very similar to what you did during lecture. And maybe actually next time we'll already start discussion about stochastic signals because we were able to solve almost everything from low pass, band pass transformations. Second. Okay, this is our problem. We have a spectrum x of f that is given. So it looks like this. This is real valued spectrum. And we need to draw spectrum in the low pass range, taking into account that we perform a transform with respect to frequency fc. Then we need to determine the corresponding signal in time domain. And we need to specify which component is in phase and quadrature. Did you do this task? I'm not sure. I think you didn't. But I think you had something similar for from repetition, from set of repetition tasks. But anyway, let's try to do it. One 1.2. But it was signal in time domain. Yeah, but here, okay. In the end, you see that all these tasks are more or less the same because they are operating on rectangulars and triangulars and yeah, very similar. But here we say that we have a spectrum and let's try to understand what happens there. So first of all, I just repeat this spectrum. And you see that we have even spectrum, it's even. Error frequency. carrier frequency, and amplitude equals to x0. We have signal x of f. And also we know that the range equals to b. No, 2b. 2b. So this is our spectrum. And now we need to find spectrum in low pass range. And nothing new. We just do all the same steps as we introduced before. So we perform transformation with respect to frequency fc. And let's follow our procedure. First, we remove negative frequencies. We remove negative frequencies. Then we normalize. First step, we remove negative frequencies. Second step, we shift our signal by the corresponding frequency. And in our case, we perform shift with respect to frequency fc. And the third step, we have to normalize amplitude. So what do we get? We get that we have two rectangular pulses centered around origin, and we have to change amplitude. So we have to increase by square root of 2 or decrease by square root of 2. Yeah, we have to increase by square root of 2 because we remove the decreased number of components in our spectrum. So we have to increase it. And that's it. This is our spectrum in low pass range. And it comes from minus b to capital B, because the range equals to 2b. 2b. Okay, and what else? Now we need to find corresponding signal in time domain, xl of t. xl of t. So we know how our spectrum in low pass range looks like. Now we need to find corresponding signal in time domain. But before, actually, I will ask you, how can we write signal? How can we write spectrum of this signal in, what's the expression for spectrum of the signal in low pass range? But yeah, when you answer, I would ask you to speak louder because I simply don't hear you. Or I can give you a microphone. We have a microphone. It doesn't work. Can we do anything with it? Okay, you can just speak louder. Sorry. Yeah, but can you name these two rectangular functions? Yeah. Yes, you're right. Now we have two rectangular pulses, but please name explicitly these two rectangular pulses. X naught, we should put also square root of 2 times rectangular No, you forget something. No. For minus, you should put something. F. F minus. Okay, now you expressing. Okay, you say that you want to express left one. Yeah. Then it will be plus. So let me change color for this, for the whole part. Then you can identify. So we have F plus, and what? So we place middle of our rectangular function. So middle will be at minus b by 2. Then it will be b by 2. And do we need to put anything else? No, we should put something, we should put information about what's the range of this rectangular pulse. How we do
By
this?
b.
Yes, we have to specify what's the denominator. So we divide by b. Okay, fine. And now let's discuss second rectangular pulse. What can you say about second rectangular pulse? I think I already made mistake. It should be minus square root of 2 times x0 times rectangular pulse, and then what should be inside argument? In this case, we have f minus b by 2 over capital B. So we have everything. We have information about shift, and also we have information about duration of our rectangular pulse. So this is how our signal in this is how spectrum of our low pass signal looks like. This formula for this spectrum. And now we have to calculate or find inverse Fourier transform. So we calculate inverse Fourier transform, and we come to time domain. So, but here it's very simple because we have two functions that we already know how to convert. And for rectangular pulse, we have square root of 2 times x0 times, and then we have b, yeah? Because if we look to our table, we see that if you have rectangular pulse in one domain, after transformation, you have to take into account this duration of this rectangular pulse, b, psi function, pi b capital B times t. And should I add something else? Have to incorporate shift somehow. We have shift in frequency domain, and we have to incorporate this shift in our time domain signal. How can we do this? We have also information about it in our cheat sheet. It's given here. So if you have shift in frequency domain, you have to multiply your signal in time domain by corresponding exponential function, by additional exponential function with corresponding frequency. So we have to add this component. So we have times exponential function j 2 pi b by 2 minus b by 2 minus b by 2 times t. Okay, and second we have plus, not plus, minus square root of 2 x0 times capital B times psi function pi capital B times t times another shift. But in this case, we have shift 2 pi capital B by 2 times t. This is how our signal will look like. And once again, have these two exponential functions, and we have minus between them. We can say that this difference between two exponential functions is nothing else as what? Minus 2j sine 2 pi p by 2 times t. Yeah? And now we can write our resulting signal in time domain. Cube square root of 2 x0 times capital B times c function pi b times t times, I had to place actually 2j in front of expression, but okay, 2 minus 2j times sine function, and we have pi, b, and t. Let's try to put everything together. So we have minus j, 2 times square root of 2 times x0 times capital B times psi function pi capital B t times sine function pi capital B and t. And this is our signal in time domain. This is how our signal in time domain looks like. And now we have to specify what is our in-phase component and where is quadrature component. Specify in-phase and quadrature components. Again, I repeat that signal in time domain. No, we don't need this full explanation. We just say that in-phase component, in our case, equals to 0 because we don't have any real parts, and quadrature component equals to everything what comes together with imaginary, everything what comes with j. And then we have minus 2 times square root of 2 times x0 times b times psi pi capital B t times sine pi capital B t. So, because we have here only part that comes together with complex number. So that's all. I think we did everything what we wanted on the low-pass band-pass transformation and band-pass low-pass transformation. Are there any questions? Minus 2, without square root of 2. Do you say that can we ignore this square root of 2? Should we place j? Oh, sorry, could you please repeat because I didn't get the question. 2 sine without sine. Shouldn't we ignore sine? Is this the question? From exponential to sine, okay. But okay, for exponential function, we have cosine alpha plus, okay, for first part, actually, we have the following, we have cosine minus alpha plus j sine minus alpha. For second part, we have cosine alpha plus j sine alpha. Minus, okay, we have minus in front of the whole expression, like this. And j comes from sine itself. And then when we calculate difference between these two parts, j will be still there. We still have j. We still have this imaginary number, and we have to keep it. We have to keep it. It's still there. We still have because, and also it's a signal in low pass range, and we can have imaginary numbers in low pass range. Okay, it was a good question. Okay, yes, more comments, suggestions, ideas. Okay, if not, then thank you for your attention and see you next week on our next tutorial. Thank you, and I wish you productive rest of the week.
Okay, sir. Where did you put these recorded lectures? Where did you put actually?
No, we didn't change anything.
No. I'm asking where do you put these recorded lectures? Recorded seminars?
Usually we don't place them. We don't share recordings. I will make available notes, but we don't share recordings. So you should attend our seminars, and this is how you get information. Yeah? But I will upload notes later today on Moodle.
Okay, thank you.
Yeah, you're welcome.
I have a question.
Yes, bye.
So
See you next week. Yeah, I mean, that's all. Thank you. If there are no questions, then we can just stop our tutorial. Yes, bye. And if you find any typos, just let me know. Unfortunately, it may happen. And yeah. Yes, goodbye.